Hi Earth, Wind, and Fire students. Today you'll be working on some plate tectonic theory activities. So here's our agenda. I'm also leaving you some pretty detailed instructions on a handout, so please make sure you work really productively so that you can get through everything today so we're not falling behind. Your homework for this evening is an official UT assignment, so please complete it and bring it to class. Next time, if you have any questions, email me or come and see me for some help. Okay. So please take notes over these notes in your notebook. So we're going to start with a question here, which you may have gotten from the videos that you watched, but after today's lesson you should be able to answer this question. So you might want to pause it and pick an answer, and we will come back to this later. Okay, so plate tectonic theory was first proposed with this idea. So South America and Africa and some of the other continents seem to fit together like a puzzle. So the big question here is, did Africa and South America once share a border? So the first person to think about this was a scientist named Alfred Wegener. And he proposed this idea of continental drift in 1912. So he was a German geologist, and he thought that the continents looked like they fit together like a puzzle. So what types of evidence would you look for to support this theory of continental drift? That's what we're going to look at today. So as evidence, one thing that Wegener looked at are fossils. So there are similar fossils in South America and Africa, and the only way those fossils could have been on both continents is if the continents were once together. There are similar mountain ranges across continents. So again, these mountain ranges couldn't have expanded the great expanse of the oceans. So the only way that these mountain ranges could have been on multiple continents is if the continents were once one big landmass. And finally, there are climate indicators. So we found, or scientists found, glacial deposits in places that are very warm today. So here's our fossil evidence. So these stripes are showing places where similar fossils were found across multiple continents. And you might want to pause this and make a note of it. So one of the big ones were the fossil freshwater reptile Mesosaurus, which was found on both South America and Africa. So Mesosaurus couldn't have swam across the ocean, so the only plausible theory is that these continents once fit together. And then there's glacial evidence. So this is showing areas where there are glacial deposits today. So places like India, Southern Africa, and South America. So as you know, all these places are very warm today. So the only possible explanation, or one of the possible explanations for these glacial deposits at such low latitudes, is that the continents were all together and they were at a much farther northern or southern latitude. So Antarctica, the southern tip of Africa, South America, India, were all together, and they were much farther south towards the South Pole, and then migrated northwards. So why and how do continents move? Is it some kind of force that's pushing them around? This is one big question that Alfred Wegener had. So he had all of these little pieces of evidence, but he could not explain how the continents actually moved around. So I want you to think about how do the continents move? Well, it's physics. So we know now that the mantle is plastic in the uppermost mantle in the asthenosphere, and the mantle convex. So this scientist named Arthur Holmes was a British geologist, and he was a big supporter of the continental drift theory, and he suggested that convection in the mantle might explain how the continents were moving around. So one big piece of evidence came during World War II, and our allies were watching to see if our enemies were testing bombs and where a German submarine could hide. So they started making these very detailed maps of the ocean floor. So this is called bathymetric data, and it basically shows the topography, or the places of high and low elevation on the continents and especially in the ocean. So this is ocean bathymetry data. So this data was collected by the Navy during World War I and World War II to look for possible places for submarines to hide and to kind of spy on our enemies. And these military data revealed something very, very interesting that we never saw before. They showed that there are mountains, essentially, underwater. And scientists had no idea that these mountain chains were there. So you can see one big mountain chain going through the middle of the Atlantic, and then there's again one over here in the Pacific. So this brought up a lot of questions. So how could we use evidence of underwater mountain ranges to further our thinking on continental drift? So I want you to think about how this could be related to continental drift and propose a hypothesis. So along comes another scientist named Harry Hess, and he proposed this idea of seafloor spreading. So he was an American geologist, and he was also in the Navy, and he proposed that those big mountain chains in the oceans, which we call mid-ocean ridges, were new rock. So new rock forming in the oceans, creating these topographic highs, or these ridges. And so some evidence that supports this are magnetic anomalies. So this dotted line right here represents one of those mountain chains, or a mid-ocean ridge. And basically we have new magma coming up and creating new rocks on the seafloor. And you can see the arrows showing these plates moving away from each other. So this is a divergent boundary. And we see magnetic anomalies. So along the ridge where new rocks are being deposited, these rocks are polarized with the current magnetic field. So this is normal polarity, and as we move away, we see stripes that are very symmetrical on either side of the ridge. So these are remnants of reversed and normal polarities. So we have normal polarity in the center, and then a little reversal. It flips back to normal polarity, a reversal, and we see this very nice pattern across the ridge. So along come two geophysicists, and they realized that this pattern of magnetic reversal was a real thing, and this supported Hess's idea of seafloor spreading. So you can see that science builds on itself. So we had Wegener introducing the first idea of continental drift, and then Hess came along and thought about this idea of the mountain chains, and that perhaps the seafloor was spreading along these ridges. And then Frederick Vine and Drummond Matthews came along, and they had some data that showed these very nice patterns of magnetic reversal to support Hess's seafloor spreading hypothesis. So at the beginning of the year, we talked about this guy Karl Popper when we talked about scientific methods, and his principle of falsification was basically that to be a valid hypothesis, there must be a test that if it fails, it will prove the idea wrong. So I want you to think about this idea. How could we, if Hess was right, what should we observe about the age of the ocean floor around these mid-ocean ridges? So I want you to think about this question. So if Hess was right about his theory of seafloor spreading, what should the age of the ocean floor be at the ridges? So hopefully you said A, the ocean floor should be younger in the middle and older as we move away. Okay, so here is a map. We're going to look at some data in just a minute. Here's a map of the crustal age of the ocean floor. So it's kind of hard to see this, but this is Africa. So the gray masses are continents. The colored masses are the ocean floor. And the red is the youngest, so there's an age scale here on the bottom. So red is the youngest, so we have the youngest ocean floor in the middle, and it gets progressively older as we move away on both sides. So there's a nice striped pattern of crustal age. So if you were Fred Vine, and if Hess was right, what testable prediction could you make about the mysterious magnetic striping on the ocean floor? So hopefully you said B, the magnetic reversals would be symmetrical parallel to the ridge. So the magnetic reversals would correlate with the ages of the ocean floor. So all of these pieces are starting to come together. So we have Wegener proposing continental drift, but he can't explain how it happens. And then along comes Holmes, who suggests that convection in the asthenosphere could make the continents move, but still no evidence to prove this. And then we have the seafloor spreading hypothesis, which we can test if we know the ages of the ocean floor. So we have dating that proves the ocean floor is younger at the ridges and older at the edges. And this helps provide evidence that mantle convection is part of moving these continents around and helps support continental drift. Okay, so I'm going to pause it here, and you're going to do a jigsaw activity. Each group is going to get a different data map, and you're going to analyze the plate boundaries, and then you'll do a second part, and then you'll come back to these notes on the rest of plate tectonics before you do your homework. All right, thanks, ladies.